Hello everyone, welcome back to another physics lesson. I'm Physics Becker, and today we're going to continue exploring motion in two dimensions. Specifically, we will look at how objects move when they are thrown at an angle to the horizontal. We'll also use vector components to help solve problems in that situation. Let's get started. First, let's review the concept of components of vectors. Any vectors can be resolved or broken down into parts along two perpendicular directions, that is, in a standard xy coordinate system. As shown in the figure, we have a vector r, which could represent displacement, velocity, or acceleration. We can break this vector into two parts, one along the x direction, which we call rx, and one along the y direction, which we call ry. Using trigonometry, the x component of the vector is equal to the magnitude of r times the cosine theta, and the y component is equal to the r times the sine theta. Next, let's quickly review what happens when you throw something horizontally. The object actually follows a parabolic path, which means it moves both horizontally and vertically at the same time. When you break this motion into components, we get a straight line motion in each direction. Horizontally, the object moves at a constant velocity. Vertically, it is free fall, meaning it accelerates downward due to gravity. Now, using the same idea, let's analyze the case where a ball is thrown with an initial velocity u at an angle theta to the horizontal. The path is still a parabola. Like before, we separate the motion into two components, one horizontal and one vertical. Since gravity only acts vertically, the horizontal motion is at constant velocity, and the vertical motion is accelerated motion under gravity, as long as we ignore air resistance. However, here's the key difference. The initial velocity has both a horizontal and a vertical component. So we resolve the initial velocity u into two parts. The horizontal component, which we call ux, is equal to u times cosine theta. The vertical component, or uy, is equal to u times the sine theta. Now, after time t, let's find the final velocity components. For horizontal motion, since velocity is constant, the horizontal velocity after time t is still u times cosine theta. For horizontal displacement, we use the equation displacement in x equals u times cosine theta times t. Now, turning to the vertical direction, the initial vertical velocity is u times sine theta, directed upward. Since gravity acts downward, means that vertically the acceleration is downward. So the final velocity is u times sine theta minus g times t, where g is the acceleration due to gravity. And the vertical displacement is given by the motion equation, u times sine theta times t minus 1/2 gt squared. Remember, the horizontal and vertical motion happen at the same time, so if we want to find the total time of flight, we can solve for t using the motion equations in either direction. And if we want the resultant displacement or velocity, we just combine the horizontal and vertical components using vector addition, like the triangular method. So what we've done is convert the curved motion in two dimensions into two straight line motions, one horizontal and one vertical, using components. This method makes it much easier to analyze and solve projectile motion problems, where the object is thrown through the air. Now, let's try an example. A ball is thrown with an initial velocity of 20 meters per second at an angle of 30 degrees to the horizontal. We're asked to calculate the horizontal distance it travels, assuming no air resistance. First, we resolve the initial velocity. The horizontal component is 20 times the cosine of 30 degrees, which gives 17.3 meters per second. The vertical component is 20 times the sine of 30 degrees, which gives 10 meters per second. To find the horizontal range, we need to know how long the ball is in the air. That is, we need the total time flight. We could try either direction, but since we don't yet know the displacement in horizontal, let's use the vertical motion instead. In the vertical direction, the initial vertical velocity is 10 meters per second upward. The acceleration due to gravity is negative 9.81 meters per second squared. since it's acting downward. And since the ball lands back on the ground, the vertical displacement is 0. Using the motion equations s equals ut plus 1/2 at squared, we solve for time t and we get 2.004 seconds. That's the total time the ball is in the air. Now, let's go back to the horizontal motion. Since the ball is in the air for 2.004 seconds, and the horizontal velocity is 17.3 meters per second, we multiply the two to get the range. So the horizontal distance is 35.3 meters. Here are the key ideas. When an object is thrown at an angle to the horizontal, it has initial velocity in both directions, horizontal and vertical. This means it moves horizontally with constant velocity and vertically under the influence of gravity. So, by breaking the motion into components, we can turn a curved motion into two straight-line motions, making it easier to solve the equations of motion. That's it for today's lesson. Thanks for watching. I hope you now have a better understanding of motion in two dimensions and how to approach problems involving projectiles thrown at an angle. I'm Physics Michael, and I will see you in the next video.